Welcome to Cell Culture Community, where we explore how science and technology can transform our health. Today, we're talking with Professor Suman Chakraborty, Professor of Mechanical Engineering at IIT Kharagpur. He applies fluid dynamics to build devices that advance health access among the underserved. He's invented tens of tools, including a portable complete blood count, handheld oral cancer imager, and infectious disease diagnostics. He's been honored at the highest levels in India for his research and teaching. So it's really a privilege to have his time today. If you enjoy listening, make sure to follow Cell Culture Community and rate this episode on your podcast platform. So welcome to the podcast. Thank you for joining us.
Yeah, thanks for inviting me for this.
So we'll get into the technical discussions, but I'm just curious while we're starting, how did you end up defining this research focus, and were you always pulled towards researching for underserved communities, or did that come along the way?
Yeah, to be fair enough, it has come along a way, not structured in the way in which it currently stands. So my research has always been emphasizing on heat transfer and fluid dynamics. So what I thought is that my study of research, which by that time had been micro and nanofluidics, that means how the fluid flows through very narrow channels, and it's a beautiful scientific subject altogether. And at that time when I started working on this research, it was something like a booming subject. There were several unsolved scientific questions, and in India in that time, our microfluidics lab that we established in IIT Kharagpur was the first microfluidics academic lab in India. Now, when I moved along the journey, usually I am a person who will always have, introspection and asking myself a question. Not like, along the tide I am moving like that. So if you look into IIT Kharagpur's, I do not know whether you have seen the picture of the main building of IIT Kharagpur. It is a very historical institute because it is the first ever IIT established right after Indian independence. But if you see what is written in front of the main building, is dedicated to the service of the nation. And this is something, which struck me, really very seriously. Because what I thought is that to be open enough and a bit of a self-critique, it is written like that, but almost everybody starting from faculty to students, they are using IIT as a platform to make their careers. There will always be exceptions, and I would rather be very respectful to the exceptions, but the general situation is that, if that connects implicitly to the service of the nation, it's fine. If not, I would imagine that nobody cares much about that. So what I thought is that whatever research I am doing and I am publishing reasonably well, can I direct it in a way so that it also helps the community? So the IIT is of course a very big campus with extremely advanced facilities, everything. But if you just go out and in a stone throwing distance within 1 kilometer, you see that the situation is not so good in terms of the basic amenities and facilities that all humans need. As a nation, our main challenge is that whenever something happens, we blame others. Government is not doing, this person is not doing, that person is not doing, and then act a bit negatively. We usually do not ask a question that what I could do in my own capacity. So that gradually brought me to the interest of developing something with the help of technology for healthcare, which can impact these people. I started getting deeper and deeper into the diagnostic technologies. And the reason is that the main challenge in the rural or even in the urban slums, it's all the same. People, they get so much less medical attention that even if they have some basic issues like hypertension, diabetes, these remain undetected for a long time. And when they remain undetected and therefore unaddressed, they can give rise to secondary and tertiary burdens. For example, someone who has diabetes and hypertension undetected for a very long time may get into chronic kidney disease. Then the burden is huge. And many times these people, because they are not always from very well to do families, they have to really take loans. Sometimes for their treatment they are losing jobs, and it not only kills them, it brings an entire family below the poverty line.
In 2022, the WHO found that out-of-pocket health expenditures push 55 million Indian families into poverty every year.
I thought that a major intervention is needed so that at least early screening of diseases could be possible. And for that, I tried to connect our research in microfluidics with the development of diagnostic technologies.
That's really amazing as a journey. And I also liked your point that we have to go beyond the default going into our scientific careers at some point and just think, where are we applying the science and why are we applying it there? Let's get deeper into your design process and engineering process after you decided to focus on underserved communities. So you were talking about some of the constraints that they would not be able to afford a very expensive test. What are some of the other kind of design specifications or parameters that you keep in mind while designing these devices?
Now, this is a very, very important question. Imagine a diagnostic test being done in the lab, what I would say resourced lab. That means resourced in every aspect. It has infrastructure, it has equipment, it has trained human resources, and it has complete environmental control. In that respect, if you have a well benchmarked high-end device or technology, it is likely to work because of the boundary conditions. So clearly our interest is that we are not going to use the lab as a primary platform for doing the diagnostic test. We will prefer to do it at the site of the patient, wherever the patient is, in a resource poor setting somewhere at his or her residence, as close to that as possible. So maybe a small center, a primary center, a kiosk, which will definitely not be as well equipped. So what are the major advantages, or what I would say as the benefits that we get when we use a lab? So we have a high quality controlled power. That means electrical power is available. You do not have dust, dirt, humidity, heat. These things are all controlled. You have trained human resources in terms of the technicians, and also better doctors will be available. You have good supply chain of materials, very important. That, for example, if you want to do a diagnostic test and you require certain chemicals or reagents, so two things are required. One is that the supply should be seamless to that remote location, and that itself may be a scientific challenge because the supply will require transportation under controlled conditions. You have heard in the COVID time that for the vaccine delivery, cold chain of the vaccines, this became so critical, and itself, people were talking about vaccines which could perhaps be stored at relatively higher temperature as compared to some others, just because the very remote locations may not always have the benefit of such good cold chain. So it is not just a business supply chain; it is also the environment in which it is transported and stored. And technology-wise, it also has to be as much as possible not only independent of all these, but also it should be very simple and user-friendly. Because who are the people who are going to use the technology? Either the patient himself or herself, which we do not imagine to be occurring on a mass scale, mostly by frontline health workers, the typical ASHA workers or equivalent. Not always they are termed as ASHA workers, but overall they are minimally trained boys or girls. Typically, you can say that at senior teenage Many of them may be school dropouts. Up to class 8 they may have studied. They can be made tech savvy or conversant with the modern technology by little bit of training, because nowadays even if there is not much high education in the per se like a structured degree, but people are very familiar with smartphones. So the whole idea is that how can we make a technology which will be effective under such extreme conditions. It will be less expensive, and it should be user friendly, and also very importantly the result that comes out of the test should be rapid. That means that you need not wait for the result for hours or days. So how do you convert a technology from its gold standard, which is like scientifically in the lab it is functioning, to its corresponding point of care version, taking appropriate technological safeguards so that it doesn't become completely erratic or its results are inaccurate. Because as I was talking about, that healthcare is such an area where inaccuracy is something which is a matter of concern.
It turns out this isn't always the case, especially for high-end technologies where the novelty factor outweighs clinical relevance. Professor Chakraborty shares an example.
I will give you a parallel in this context, that there are many high-end technologies where the technology is so much mind-blowing that we do not care much about the accuracy. Classical example is use of smartwatch for many health purposes. So when smartwatch is giving us something, how many of us are really bothered about the accuracy of the data? We are very much happy that smartwatch is giving this and that, and it becomes more like a technology marvel. But if you speak to any doctor and say that, doctor, I have smartwatch data, can you use this for my treatment? So doctor will say, okay, you have this data, but I have to use my own sort of judgment or test. This is very common. I mean, I have not seen any doctor treating on the basis of smartwatch. It may be good for a patient for self sort of awareness and screening, or maybe good lifestyle practice, but it cannot be considered as a clinical benchmark. So we have to be very careful that when we are replacing a clinical benchmark with another technology, that also should be a clinical benchmark with whatever inaccuracy, but it should be statistically well documented.
There's a rich innovation ecosystem around point-of-care diagnostics.
It is a very, very active research topic, and people have been working on this over the past several years, at least a decade, including industry. But what you will find is that the point of care diagnostic space did not make that kind of dent as compared to the market need which is existing. So there is a huge gap between the demand and the supply. So why is it happening?
Like smartwatches with their lower accuracy, a majority of commercial point-of-care tools lack one or more of the design criteria necessary for them to be useful for clinical decision-making in a low-resource context.
Some of the reasons could be that the technology is point of care. That means it's like a small, portable thing, but it may be expensive. It could require auxiliary items like materials, etc. And it might not be that user friendly. It might require power to run. So all in all, those point of care technologies are simplified as compared to their lab counterparts, but they are not drastically simplified to an extent that they would work for the bottom of the pyramid. So this is known as extreme point of care diagnostics. Point of care diagnostics, you are familiar with, say, the at home glucose blood sugar test, pulse oximeter, thermometer has been existing for a very long time, the digital thermometer. So these are point of care devices. Even these ones are not so easily adaptable in extreme resource poor settings. These are common household applications for those who have good sort of home condition. So I will go one by one. What are the boundary conditions? In fact, WHO has something which is called as an assured criteria, ASSURED. I will not go into the full acronym, but what it basically means is that it has to be affordable, accessible, and it should be rapid, low cost, and it should use minimal device technology, and it should be user friendly. And it should basically be capable of working in all weather conditions, and it should be integrable with whatever advancement in digital and communication technology has been made.
Interesting. Yeah, we have to really think about we can write a paper and say 7 out of 8 criteria are met, we can be happy with ourselves. But if the last criteria is the one which is blocking the usage, then it's still a problem.
Yes. And the major issue is that that if any one of these remains vulnerable, you will find the technology so good in terms of working in the lab. You can publish outstanding papers in very reputed journals, but you will find that that technology doesn't work on the field. And I would say, with all due respect, more than 90% of point of care diagnostic technology innovations are like that. You will see glamorous papers, but many of them will require a lot of further adaptation.
90% is a crazy number. It was interesting hearing about Professor Chakraborty's boundary conditions. I've seen some of them before, but weather and supply chain really stuck out to me. Heat, dust, and humidity vary sharply across different parts of India and across the year. And the class of diagnostics I worked on during my undergrad thesis was extremely sensitive to contamination. Also, rising temperatures have come with more and more frequent power outages in Delhi every summer. I can only imagine how this will affect cold chain stability in the future. In the next part of this conversation, I wanted to learn what engineering techniques his lab uses to adapt diagnostics to meet these design constraints. What are some of these techniques that you apply to meet these design criteria?
So our lab has been working very closely on paper microfluidics. I will tell you, how the motivation comes. Of course, one of the motivators is the living legend himself, Professor Whitesides from the Harvard University. If at any point of time I have some opportunity to discuss this with Professor Whitesides, I will clearly tell that how the work of a scientist can motivate next generation scientists. But the general motivation, imagine how a blood test is done normally. So people will sort of have a big syringe and maybe have a tubing wound on your arm to get the vein and then get the vein punctured, and syringes full of blood depending on how many tests you are doing. And most of these tests will require a significant amount of blood. So you may ask, so what? Blood will not cost. But now there are two angles. Number one, say pediatric patients, young children. For them, taking that amount of blood is not a matter of joke. And once they grow up, you find that children become more and more resistive to all these until and unless they become significantly mature and they realize that it's a phobia for injection and all those things are there. It's just a mental comfort. But leaving that apart, technology wise also, if you now imagine that how we will do that test, let us say we do a biochemistry test. That means the reagents reacting with blood will give a signal. It may be a spectroscopic signal, it could be a color signal. When you have a sort of a simple setup, you can see the change in color, just like a pH based system. So now the question is, if we use one drop of blood, whatever volume of the reagents is required is much less than if we do one syringe of blood. So less amount of reagent means less cost. And also less amount of reagent means that you can make a tiny miniature device, a small device on which you can organize all your lab activities. This is known as lab on a chip. So the entire processing lab, which could have all the elements a resourced biochemistry lab will require, condensed in a small, not literally a chip, but maybe a small tabletop or maybe a credit card type of unit. So there you drop the blood, you may have reagents, blood will react with the reagents, there may be a change in color. If you want to do that, you have to imagine that when you put the blood will spread in any sort of platform. And if you have your reagent stored at a certain place where you want the blood to react and your focus, say your spectroscopic exam is focusing on that, so the blood has to go to that place. So in the lab, what you do, you use a pump to pump the blood, through a channel. In a resource poor setting, you would not like to use any electrical power or a pumping device, because these are auxiliary devices. They require their maintenance, not just a cost. It is like inconvenience in terms of availability of resources. So what would be if you do not require that pump, but you have a natural pump by which it can happen? So that natural pump in the science of microfluidics is capillary action or surface tension.
He explains how capillary action works.
All of us have studied in the plant life science in school. In the ground, you have the water and the nutrients in the soil. And if you have a tall tree, you see that the uppermost branches or leaves, the water will be sucked and pumped to. Whereas if you want to lift the water by that height in your house, you will require a pump, right? So why you are not having to require a pump? The reason is that you have tiny capillaries, and tiny capillaries, their surface tension force is so strong that it can overcome any other gravitational pull and lift water or any other nutrient along with the water. But the catch is that to use that, you require tiny capillaries. And typically, those capillaries are micron, that is micrometer. So, what is the typical size? You can imagine human hair, its thickness is something like that. Now, you have to make such a thin channel in a material, be it plastic or glass. And why plastic or glass is because it has to deal with biological fluids. So it has to be biocompatible. If you have to engrave these tiny channels, that becomes quite a challenging job, because it again requires a lab resource, and a very, very unique lab resource, which we call as, in the semiconductor industry, fab lab. That is where we make these integrated circuits. Very similar facilities are required. So you imagine that on one hand we are talking about a simple technology, but its fabrication, if it's very complicated, how can people get the benefit of that in terms of scalability, where such facilities are not available?
This is where paper as a medium comes in. Surprisingly, it's biocompatible with a variety of fluids.
One of the possible resources could be to use a frugal, simple platform, and Professor Whitesides introduced paper as a platform. So the paper has many such narrow passages. If you take a scanning electron microscope image of a paper, you will see that the paper has a cellulose network. There are random cellulose fibers, and they are connected by small pores. And they are not really regular pores, but small pores. And through each pore, what is happening is the microfluidics that I was talking about. That is the flow through microchannels. But it is not so easily controllable. If you drop a fluid, it will randomly diffuse. So you require to make that microchannel.
Microchannels also allow us to run multiple tests with one sample and create complex circuit-like logic on paper. For a long time, these channels were created with techniques like wax printing and photolithography, more accessible than a fab lab, but still needing specialized tools and chemicals.
When we were working on microfluidics, I used to actually visit many places for outreach, including schools and small colleges, which do not have the luxury of having the IIT-like facility. So many times after my talk, maybe a student or maybe young teacher would tell me that, well, Professor, you have told something which is interesting, but the question is, we do not have any kind of facility to work on it. So for us, it is like a science fiction story. Doesn't exist, or we really do not have any scope of doing this. So this actually haunted me very seriously. And then what we did is, this is roughly 10 years back, we developed a technology whereby simple printing, using our office printer, we can make microchannels on paper. So what in a microchannel you require is a barrier. So imagine you are drawing a channel. So you make thick borders, and these are channels. So if you make it in a CAD software and print it on a paper using any office printer, you get your channel. But the thing is that it will not work in practice because that barrier is not a, you can say, a durable barrier. So what we did is that we used that office printer to print that borders, and then we heated that paper on a hot plate at about 200 degrees centigrade for 4 to 5 minutes. It appears to be something as if it is heuristic, but it's not like that. So when you have a printer, it has a toner, very well, that and the toner particle which comes out of it, it actually has hydrophobic characteristic. That means it has a phobia for water. But those particles will not normally deposit deep into the pores of the paper where you really want to make the barrier. But if you heat the paper at that optimal temperature under optimal condition, the toner particles will melt and block the pores. Once you sort of cool it, it gets solidified and it becomes permanent. You do it on both the sides of the paper, and in that way, by having simply a printer and maybe a computer, which every place now will have, without any lab, you have a micro channel made on paper. So that is the first thing that we did. So this is designed for manufacturing.
How truly innovative. Professor Chakraborty applied simple scientific principles to find a really deep chemistry and use within the toner particles in our everyday home printers. Finger pricks replace blood draws, capillaries replace pumps, paper replaces glass, and home printers replace fabrication labs. It's taken tens of scientists decades to pull all this together. The lab-on-a-chip dream is to be able to precisely and efficiently translate any lab process or test onto paper chips and distribute them at scale. But there's still so many components, from centrifuges to color analyzers, that are difficult to adapt. Next, Professor Chakraborty shares some of his work in this space.
So this design worked, and of course this is not scalable. You can do it as a school project, but you cannot really make it large in number. So subsequently we made an automated machine which could do all these things like cutting a paper, depositing things and packaging it all in a mechanized way. But the entire motivation comes from that simple art and craft we do in our junior schools. Now there are many things. First of all, there are many blood tests where you do the test with just the watery part of the blood, which is called as plasma. So, for example, if you go for a blood sugar test, they give plasma glucose. In our home glucometer, they have the whole blood glucose estimate, and they have a mathematical correlation from which they relate it to the plasma glucose. But it is not a direct plasma glucose, because plasma glucose will require a separation of the blood cells from the watery component. So what we had to do is to make a small membrane filter and embed on the paper, so that the whole blood has about 40% red blood cells. So that is segregated. The plasma will flow by capillary action, and it will go to the test spot where the reagents are there. So that it will react and a color change will take place. And the color change is something which is still very subjective. So what we did is, we tried to take a picture of that color spot with the help of a very controlled imaging system. We created a small portable box in which we had basic electronics and optics, where you have illumination. So after the test, we used to insert the paper strip into that device, just like how we insert a credit card to a credit card. What would happen is that the device itself has a controlled illumination. The spot where the reaction is occurring, it will highlight that spot. And then by a camera, typically we always prefer device integrated camera, because it has a stable optical condition. But we also started using smartphone camera. So in that way we tried to adapt the smartphone to take the picture. With the smartphone you have the digital data or any other digital camera. So we decoded that digital information by something which in the technology is known as image processing. You quantify the pixels with certain numbers depending on the color, intensity, other features, pattern maybe that you see. So with that, we get a quantified description of that color, and the same drop of blood, if you do a test in the lab where we send our normal samples for the diagnostic testing, it will give a report. So you have a table on which you have digital numbers, and on the other column you have the correct value of the glucose. So in that way you can have a calibration chart mapping. So this can be done by a simple mathematical function, but simple mathematical function may not be able to capture so many variations that you get in human patients. So if you have large number of such data with a wide variety of patients, you reflect that by training your algorithm so that you have a mobile app which can predict it, that is done by something which is called as machine learning. So you see how the things are progressing or have progressed from that early advancement of microfluidics as a science to a complete device which uses microfluidics, optics, electronics, up to machine learning and data sciences.
And still in a very simple form factor.
In a very simple form factor. So that became our first technology. We validated and used and all this, but I am always a high level of self-critic individual. So what I thought is that these are good, but still I am requiring a device. Imagine I am a patient who needs very intense regular monitoring of my sugar or hemoglobin for anemia. So can I carry that device? Forget about the cost. Can I have those reagents needed for doing the test? So can we make it device free and without any reagent? We then made a tie-up with an industry and started adopting a technology where we have the simple strip which you carry in a pocket, and you do not require any liquid reagent because the reagent is solid reagent is embedded there, which is known as lyophilization. You just carry some of these small needles, lancet needles, which come with a glucometer. Carry those in your pocket or backpack, these strips, and you already have a smartphone, and you do not require anything else. So we tried to make the smartphone all in all, and tried to apply AI and coding more and more, so that the challenge with the technology that every smartphone has a different camera, the background illumination, the lighting condition would be different, user will be very erratic. So we tried to have the app by taking all these factors into account to a large extent, that now we have, and this is just maybe a 1 year old phenomenon or even less than that. Now we have a technology which is a group of technology known as smart QR, and a couple of these technologies have already got approved commercially, and they are going to come to the market. So you now have a strip which you carry in your pocket, that paper microfluidic, that lancet set of needles, and your smartphone. So you are there in the rail station, airport, in the marketplace, and you want to monitor your health. You can do it absolutely anywhere and without requiring much of the boundary condition. And the entire effort is that be it simple, but let it not be that inaccurate. Now you have to imagine that this cannot be as accurate as the lab test. If someone says that I claim, that claim is not correct. So all what you have to do is to make sure that your technology is within certain errors of what you get in the lab standard, so that the doctor has a confidence. And many times doctors will not really require 1 decimal or 2 decimal accuracy. Broadly, if they have the number, they can start your basic screening or intervention on the basis. So that I would say, as a journey that was there from there to here.
I was in awe of how far Professor Chakraborty pushed the idea of minimal resources, with instrument-free tests that are usable on the go. Well, not really instrument-free. His team intelligently used smartphones, arguably the most advanced device that's affordable and accessible at scale today. Though it feels disconnected, this win belongs in part to the engineers that helped drive down the cost of microchips over tens of years to a point where over 70% of households in India have a member with a smartphone today. In the last part of this conversation, we get a little personal. Professor Chakraborty has worked on so many diseases and techniques over his career. I ask him which one innovation he's most proud of.
So I will talk about actually two innovations I am very proud of. One, impact in terms of simple science. You can say simplicity with very deep science. So I would just tell it in a very brief way that when you are moving that say drop of fluid as it moves along the paper, it is the capillary action I explained. But capillary action is not that fast. So you want a rapid test. If you could control it in a way that it moves faster, and the same stream of blood flows into different directions with extreme control, so that at different spots you do different tests. For that, what we try to do is to use an electric field. If you apply electric field, because of certain phenomenon which scientifically is known as electrokinetics, you can have movement of the blood with the help of electric field. Now that means, again the challenge, you have to make electrodes on that paper or whatever. And electrode deposition is a very, very, what I would say, sophisticated technology in the fabrication world. So what I told to my students is that, can you try by making pencil sketches on the paper? As that graphite and that lead of the pencil, and that was something which came to my mind. But you know that you have also been a student. That students will have a particular way in which they would consider the advice of their advisor. Sometimes they take it as a madness. They may not express it because of the extreme polite behavior. But I could see that sense that in my students who are working on that. So I almost enforced them that you please do it, and they did it, and they found that it worked. So that simple HB pencil sketched on the that paper, that acted as an electrode, and then if you connect it with a wire and put a simple power source, you will see that electric field is driving that capillary fluid much faster. So this was the first invention in the world from our microfluidics group, and this is known as paper and pencil microfluidics. And I am very happy and proud about it, not just because we invented it. I see large number of people all around the world not only have adopted this, but actually have improved this to a large extent. So in that way, it had set up a new direction of microfluidics research. Now coming to impact on people, the most satisfying one has been the oral cancer screening technology that we have developed. We all know that oral cancer is a major problem in many settings where it is because of typical tobacco consumption habit or chewing habit. It could be due to indirect factors like HPV, virus infections. So it need not at all be related always to that chewing habit, but a majority of that is due to such habits. In the extreme underserved conditions, people tend to consume this and they develop a kind of condition inside the mouth which appears to be very benign and initially not much of a problem. This is known as oral submucosal fibrosis. In a loose term, we call it precancer. The medical experts who can actually look into that early and get it corrected, they do not exist in such underserved settings. So these people remain undetected till that precancer becomes cancer, and this sometimes happens almost silently. So if you could catch them early, if it is early cancer, fine. I mean, you can do a lot of good intervention. If it is pre-cancer, you can completely reverse. It's even better. But what we found is that the devices or the technologies which can do imaging and come up with such recommendations, be it MRI, CT scan, these are not something that you can talk about for these people. You have simple optical intraoral cameras, but they are not good for this. So what we did is that we developed a torch type of handheld device where we put a thermal camera and take picture inside the mouth, non-invasive. It doesn't hurt anything. For about 30 seconds, is taking the picture, and we have developed an algorithm which is like our patented technology, where we convert that temperature data, that thermal imager is taking to blood perfusion data. That means how locally blood is flowing with quantitative numbers. And when there is early cancer, there is angiogenesis, new blood vessels form. In some point of time, you can have necrosis, complete blockage of blood flow. So many things can take place. Physiologically, it is known. And then by using machine learning and training with patient data, we could map this result with whether the patient has pre-cancer, cancer, or normal. And this we made field trial, first round of clinical trial in Guru Nanak Institute of Dental Sciences and Research, and we got very promising results. And this was one of the very high impact publications also in the PNAS. This is a technology which has made me very, very optimistic. We are now in the process of its ground implementation, and I believe that large number of patients who were not earlier in the ambit of early cancer screening would benefit from this.
To hear more about AI-based cancer diagnostics, check out my previous episode on a breast screening tool that's already made it to the market. We dive deeper there into algorithm design and data curation.
Tobacco chewing is so common in certain parts of India that one can imagine the disease burden. I don't even know if it's quantified properly. It's really great to hear about all this, Professor, both the scientific impact, because, there you don't know, it will spin off so many other things, and the device. So we actually initially got connected because of that device to implement it in another field setting. So usually the last question that I ask to end is a bit simple, just about yourself. What's something simple you do for your own health or health of your family and community, just away from all this big science and tech?
Yeah, I mean, what I say is that it is very difficult to do anything which you feel is foolproof, for your health or for your family and your friends and neighbor. But what I try to do is one thing, that try to have a very simple approach of how life goes. It is very important for me that more you complicate. You develop algorithms for technology, but do not develop algorithms for yourself and interacting with others. This is what is my motto. Just keep it simple. Keep your mind simple as a child. I am perhaps as curious as I used to be in my very early days. And when I see my son, he's in school, and I find that I'm still as curious in many ways as he is. And perhaps he has more answer to those queries because he has the access of the smartphone and the internet, YouTube, etc. And I try to introspect more and try to be more curious, more simple, and try to apply that simplicity in terms of human interaction and how I communicate with people, and how I also look into the aspect of health. Not too complex, not too much bothered about every time measuring this and that and all, and just try to have a simple lifestyle, try to have a control in everything, and that's it. Then there are certain things which are beyond your control, they can happen, but that's it.
Thank you. It's really inspiring to learn from your work, and especially very rare such projects which are scientifically at cutting edge as well as so impactful.
Thanks so much, and looking forward to further interactions at some other point of time.
Thank you for listening. If you like this episode, leave a rating and review wherever you get your podcast. Follow us for more conversations on how bioengineering can transform human and planetary health. Till then, breathe deep, stretch something that feels stiff, and look around. Notice something curious, delightful, or in need of care. We are gifted with so many chances to love and wonder every day.